Why are parallel RLC circuits crucial for AC analysis? Imagine trying to tune a radio or filter out unwanted noise from an audio system. You are actually working with circuits that behave very much like the parallel RLC circuits we're about to explore. These circuits are key in understanding how electrical systems respond to alternating current. They help engineers figure out how voltage and current change when resistors, inductors, and capacitors are connected in parallel. This knowledge is essential for designing everything from radio receivers to power systems. In a parallel RLC circuit, the voltage across all the components is the same at any moment. This makes analyzing the circuit easier because instead of looking at how current flows through each part, you focus on the voltage. The current then divides among the resistor, inductor, and capacitor based on their individual properties. This division depends on something called admittance, which combines conductance and susceptance. It's like a measure of how easily current can flow through each part, considering both resistance and reactance. Using admittance makes it straightforward to calculate how much current goes through each branch and how they all interact. One of the most important features of these circuits is how they behave at different frequencies. They have a special frequency called the resonant frequency, where the inductive and capacitive reactances cancel each other out. At this point, the circuit acts as if it is purely resistive, and the total impedance is at its lowest. This is very useful in tuning circuits, filters, and oscillators because it allows engineers to select or block specific frequencies. When the circuit is at resonance, the current can become very large, which is why these circuits are also used in radio frequency applications. Phasor analysis is another tool that makes working with parallel RLC circuits easier. It uses complex numbers to representing sinusoidal voltages and currents, helping us see the phase difference between them. This is important because in AC circuits, voltage and current often do not peak at the same time. Understanding these phase relationships helps in calculating power and designing circuits that minimize energy loss or improve efficiency. These circuits are everywhere in real life. They are used in radio tuning to match impedance between different parts of a system and to improve power factor in electrical grids. They also help in designing filters that block unwanted signals or noise. By applying Kirchhoff's current law and the current divider rule, engineers can systematically find out how much current flows in each branch at any frequency. This makes predicting how the circuit will behave under different conditions much easier. In short, parallel RLC circuits are fundamental tools for AC analysis because they show how resistive and reactive elements work together when connected in parallel. They help us understand resonance, phase relationships, and how to control and manipulate signals in electrical systems. This understanding is vital for designing efficient, reliable, and precise electrical devices and power systems.